In question 1, we are told that at time t is 0, a small stone is thrown vertically upwards with a speed of 14.7 meters per second from a point A. Now at capital T seconds, the stone passes through A moving downwards. We are modeling the stone as a particle moving freely under gravity, so we are neglecting air resistance throughout the motion. And using the model, we need to find the value of capital T. As always, I will start by drawing a diagram to illustrate exactly what's happening. So we've got the point A, it's higher above ground. We are throwing the stone upwards and then it comes down. That's the vertical motion. I'm gonna open up this motion like this so that I can illustrate all the necessary information in a clear way. So this is what's happening. We've got an initial velocity of 14.7 meters per second upwards. The acceleration is negative g because the gravity is fighting motion, and we are told that at capital T seconds the stone passes through A. So at capital T seconds we are on the same height as A, so something like this, and I will be using Suvad equations here to determine the value of capital T. Now the first thing I can do is exploit the symmetric nature of vertical motion. So since these two are on the same height, it means that the velocity here is negative 14.7, so exactly the same magnitude but different direction. So I'm gonna say that v is equal to u plus at. So at this point here the velocity is negative 14.7, which is equal to the initial velocity of 14.7 plus the acceleration of negative g times the capital T. So we've got negative 14.7 being equal to 14.7 minus gt, which leads to gt being equal to 29.4. Now we know that g is 9.8, so 9.8 capital T is 29.4. And if I divide both sides by 9.8, we arrive at capital T being equal to 3. Now, alternatively, we could have considered that when T is capital T, the displacement is 0 because as the stone is thrown up and then it comes down, then the moment we are again at A, the displacement is 0. So I could have used that S is ut plus a half at squared. So the displacement from the point A is 0 because we are exactly at the same place. So 0 is equal to 14.7 capital T plus a half times the minus g times the capital T squared. So we're looking at 0 being 14.7 capital T plus a half times the minus 9.8 times T squared. So we have 0 is 14.7 capital T minus 4.9 T squared. I will factor out the capital T. So we're looking at 0 being capital T times 14.7 minus 4.9 capital T, which leads to T being 0. Or alternatively, we've got that 14.7 minus 4.9 capital T is 0, which means that 14.7 is 4.9 T. And if I divide both sides by 4.9, I arrive at 3 being equal to T. And I also need to reject the T being 0 because we know for sure that T has to be positive. So we end up with exactly the same answer, that T is equal to 3. In part B, we need to find the total distance traveled by the stone in the first 4 seconds of its motion. So let's refer to the diagram once more. We have already found that capital T is equal to 3. And I can exploit the symmetry that halfway through I'm attaining the maximum height. So when T is equal to 1.5, now I'm trying to find the total distance during the first 4 seconds of its motion. So when T is 4, I'm somewhere here, and I will start by considering the journey upwards, this part here. So I'll be calling this distance D1, and then I'll be considering the journey from the maximum point down to T being equal to 4. So in this case, this is the journey we're considering. I will consider this as a new equation of motion. So I'll be setting my T is 0 to be here exactly at the maximum point. When I arrive at T is equal to 4, then this corresponds to T being 2.5 because from 1.5 seconds up to 4 seconds, we've got a span of 2.5 seconds. And for this motion here, I will consider the initial velocity being 0 and the acceleration being g, and I will find the distance d2 here. So the total distance traveled will be d1 plus d2. So I'm splitting the journey into the upward journey and then the downward journey. So for the upward journey, the acceleration is negative g because gravity is fighting motion. However, for the downward journey, the acceleration is g because it is acting in the direction of motion. I will proceed with s being ut plus a half at squared to find d1 and then d2. So we've got that d1 is equal to 14.7 times the 1.5 plus a half times the negative g times the 1.5 squared. So d1 is equal to 14.7 times 1.5 plus a half times the negative 9.8 times 1.5 squared. And if I plug this on the calculator, get that d1 is 11.025 meters. And I will proceed for d2. Now for d2, I will be using again s is ut plus a half at squared. However, u is going to be 0, t is going to be 2.5, and the acceleration will be g. So we are looking at 0 times 2.5 plus a half times the g, which is 9.8, times the time, which is 2.5 raised to the power of 2. This gives an answer for d2 of 30.625 meters. And therefore, to find the total distance, all I need to do is add the two distances we just found. So we're looking at 11.025 plus 30.625. This gives an answer of 41.65. If you give this as your final answer, you will be penalized because using g to be 9.8 means that we need to give our final answer to 2 or 3 significant figures. I'm always giving to 3SF, so this is going to be 41.7 meters. In part C, we need to state one refinement that could be made to the model apart from air resistance that will make the model more realistic. The first thing we could mention is using a more accurate value for G, and we could also take into account the dimensions of the stone, because modeling the stone as a particle means we are completely neglecting its dimensions. In question 2, we've got the particle P moving along a straight line. The velocity v meters per second is given here in terms of the time t and k being a constant, and we need to find the acceleration of p at time t seconds. Now we know that the acceleration is the derivative of velocity with respect to time, so it's dv dt, which is equal to 10 minus 2t. Now the particle P is instantaneously at rest when t is 6, and we need to find the other value of t when P is instantaneously at rest. So we know that when t is equal to 6, the particle is at rest. So when t is 6, v is 0. So this means that 0 is equal to 10 times 6 minus 6 squared minus k. So I have substituted t is 6 into the expression for v. This will help me determine the value of k. So we're looking at 0 being 24 minus k, and therefore k is 24, which means that the expression for the velocity is that v is equal to 10t minus t squared minus 24. Now I'm trying to find the other value of t for which p is instantaneously at rest. So we need to solve v being equal to 0, which means we're looking at 10t minus t squared minus 24 is equal to 0, and therefore 0 is t squared minus 10t plus 24, which factorizes into t minus 4 times t minus 6. So we've got t minus 4 is equal to 0, or t minus 6 is equal to 0, which means that t is 4 or t is 6. Well, t is 6 is the value already provided by the question. So what we are looking for is t being equal to 4. Now in part C, we are asked to find the total distance traveled by P in the interval of 0 to 6. So the total distance traveled during the first 6 seconds of motion. Now we've got the expression for the velocity here. I'm about to sketch this. I'm looking at the quadratic with a negative coefficient for the quadratic term. So it's a sad face parabola. It's cutting the horizontal axis, the t-axis at 4 and 6, because these are the values of t we found in part B, for which the particle is momentarily at rest. So the graph of the velocity against the time looks something like this. We're trying to find the total distance traveled in the first 6 seconds, which is given by the area between the curve and the t-axis between 0 and 6. Now I will split this into 2 separate areas, the one below and the one above, because if I integrate from 0 to 6, this part here being below the horizontal axis will contribute negatively, and the final answer will not be the true distance traveled in the first 6 seconds. So what I'm going to do, I'm going to call the first area here A1, the second area A2. I will find them independently using integration, and then I will add them up. So to find A1, I will be integrating from 0 up to 4, 10t minus t squared minus 24 dt. Now in integration, we increase the power by 1 and we divide by the new power. So it's 10t squared over 2 minus t cubed over 3 minus 24t, and the limits are 0 and 4. Now before substituting the limits, we can simplify the 10 with the 2, leaving me with a 5 here. And I will substitute the upper limit, so it's 5 times 4 squared minus 4 to the power of 3 over 3 minus 24 times 4. And if I substitute the lower limit of 0, we can see that everything is 0, and therefore the overall contribution by the lower limit is 0. And if I plug this on the calculator, I get an answer of minus 112 over 3. We are not surprised that we got a negative answer, because the area A1 lies entirely below the horizontal axis. And then we can proceed with A2. So again, we are integrating from 4 now up to 6, the 10t minus t squared minus 24 dt, which is equal to the 5t squared minus t cubed over 3 minus 24t. The limits are now 4 and 6. We will begin by substituting the upper limit of 6. So we are looking at 5 times 6 squared minus 6 cubed over 3 minus 24 times 6. And then we will substitute the lower limit of 4. So it's 5 times 4 squared minus 4 to the power of 3 over 3 minus 24 times 4. Now we plug this on the calculator, we get an answer of 4 over 3, and I can proceed in finding the total distance traveled in these first 6 seconds, which is going to be given by the 112 over 3 plus the 4 over 3, which is equal to 116 over 3 meters. In question 3, we've got the ball P of mass 2m attached to one end of a string. The other end of the string is attached to a ball Q of mass 5m, and the string passes over a fixed pulley. Now the system is held at rest with the balls hanging freely and the string taut, and the hanging parts of the string are vertical, with P at a height of 2h above horizontal ground and Q at a height of h above ground. Now the system is released from rest, and in the subsequent motion, Q does not rebound when hitting the ground and P does not hit the pulley. Now the balls are modeled as particles, with the string being light and inextensible and the pulley being small and smooth, and we are completely neglecting air resistance, and we need to write down an equation of motion for P and an equation of motion for Q. So the first thing to do is go to the diagram and add all the forces acting. We will start with the weights. So for P it's 2 mg and for Q it's 5 mg. We've got the tension pointing upwards for both P and Q, and since P is the lighter of the two, it will be accelerating upwards as shown here, and Q will go down, so it's accelerating downwards. So the two accelerations have the same magnitude, and therefore we can proceed. We will consider P here. P is accelerating upwards, so forces acting upwards, which is T minus forces acting downwards, which is 2mg, is equal to mass of 2m times the acceleration, which is a. Whereas for q is accelerating downwards, so forces acting downwards 5mg minus forces acting upwards, which is t, is equal to the mass of 5m times a. Now in part B, we need to find, in terms of h only, the height above the ground at which p first comes to instantaneous rest. So this is the diagram we had before. These are the two equations of motion. I can combine the two together and add them up to eliminate t. This leads to 3mg being equal to 7ma. Obviously the m will cancel out, and therefore we conclude that 3g over 7 is the acceleration. And therefore we can proceed into considering exactly what will happen once the two particles are released from rest. So this is the initial position of p and q. P was 2h meters above ground. Now as q goes down, it will hit the floor by descending by h meters. So p will go up by ascending by h meters as shown here. At this moment, the string goes slack. There is no longer tension in the string. And then we've got movement under gravity. We've got motion under gravity as p makes a final jump, reaching its maximum, at which point the velocity will be 0. So we're trying to find this extra distance d, so that the maximum height that p will attain above ground will be the 2h plus the h plus the d. So for this last leg of the journey, we've got motion under gravity. Now we'll start by considering q when it hits the ground, because the speed with which q hits the ground is the same as the initial speed with which p begins the motion under gravity here. So I'll be using v squared is equal to u squared plus 2as. The system was released from rest, so u was 0. So we've got v squared is equal to 0 squared plus 2 times the acceleration, which was found to be 3g over 7 times the distance covered, which is h. So we've got v squared is equal to 6gh over 7. And therefore we conclude that the speed with which we hit the ground is 6g over 7 square rooted. And this is exactly the same speed with which p will start the final leg of the journey. Now we'll proceed by considering p when the string goes slack, and the initial velocity of p is exactly the speed we found for q when it hits the ground. So we've got that u is equal to the square root of 6gh over 7. We've got that the distance covered is d. We've got that the acceleration is negative g. We know that at the maximum point v will be 0, so we will be using Suvat again to find the distance d. So I'll be using v squared is equal to u squared plus 2as, which takes me to 0 squared being equal to 6gh over 7 square rooted and all squared plus 2 times the negative g times d. This leads to 0 being equal to 6gh over 7 minus 2gd, and therefore 2gd is equal to 6gh over 7. I will cross out the g. I will simplify the 2 with the 6, so we get that d is equal to 3h over 7. This is the extra distance covered while moving under gravity. It's the distance here. So the total distance we're trying to find, it's going to be d plus h plus 2h. So let's do the calculation here. We've got the total distance covered by this particle being equal to 2h plus h plus 3h over 7, which gives an answer of 24h over 7 meters. Now in part C, we need to state one limitation of modeling the balls as particles that could affect our answer to part B. Now modeling the balls as particles means that we're completely neglecting their size, their dimensions. So when Q hits the ground here, we are assuming it's just a dot, whereas in reality we know it has a certain size. So the answer here would be the distance that Q falls to the ground wouldn't be exactly h, simply because of the dimensions of Q. Now, in reality, the string will not be inextensible, and we need to state how this would affect the accelerations of the particles. So the assumption that the string was inextensible means that the magnitudes of the accelerations of the two particles will be exactly the same, because as one moves, the other moves in exactly the same way, but in exactly the opposite direction. But if it was the case that the string was not inextensible, then the magnitude of the accelerations of the two particles will not be the same.